Imagine a population of users navigating across a connected network of web pages. At any point in time, every individual user has a choice to randomly pick another link to visit. The question we're going to focus on today is how one might define a ranking of pages based on a model of the web network. The particular model we'll focus on in this video is called a Markov chain, and what we'll eventually build to is an understanding of a remarkably beautiful algorithm called PageRank, which formed the backbone of Google search. As we like to do on this channel, we'll approach PageRank from a discovery-oriented perspective, where we'll naturally interact with powerful mathematical ideas involving these Markov chain models. Let's get started. A Markov chain is defined by a few specific properties. In the context of our web network, individual web pages correspond to states of the Markov chain. And going from state to state involves a transition probability. In this particular network, any user can go from state 3 to state 1 with transition probability 0.5. If a user is at state 2, they have a 100% chance of transitioning to state 3. In the context of web networks, it's common for transition probabilities to be assumed based on the number of outgoing links. For example, if a web page has 3 outgoing links, we assume the user is equally likely to transition to each of the states with probability 1/3. It is possible to also alter these probabilities based on some prior knowledge or data. So if we change the distribution as follows, it would assume that users are much more likely to click on an outgoing link to web page 2. Now the problem we care about today is ranking the importance of states in the Markov chain. A simplified real-world use case here is to imagine a user got 4 web pages from a search query. These web pages will often reference each other, so they form a Markov chain. How should we rank the web pages to show an end user? The first question here is how we should define the importance of a state in a Markov chain. If we have a variety of users surfing web pages, what might be a good way to rank the relative importance of each web page? Well, one natural way to think about the importance of web pages is to imagine a single user continuously going from page to page according to the Markov chain model. At each point in time, the user is going to be at a particular state of the Markov chain, and we could maintain a counter for the number of times they visit a state. Over a long period of time, the states that end up being visited more often can naturally be thought of as having a higher rank. In fact, rather than counts, we can think of this long-term behavior as a distribution on the proportion of time a single user spends in each state. In this particular Markov chain, if we run this experiment for a long period of time, the distribution stabilizes, and this distribution is formally called a stationary distribution of a Markov chain. Here, the stationary distribution indicates that the most important state is state 2, where the interpretation of the probability is that a random user who surfs this network for a long period of time will spend about 26% of their time at state 2. What we're going to dive into in this video is how exactly might we find a stationary distribution of a Markov chain? In what conditions do these stationary distributions even exist? How do we efficiently compute them? To get into how we calculate stationary distributions, we have to first understand how we can model Markov chains mathematically. At its core, a Markov chain is a random process involving steps in time. A user might start at some initial state, and at each step, according to the model, they randomly transition to one of the possible next locations. At every step in time, there's a probability of a user being in a particular state. A natural way to model the state distribution at a particular step n in a Markov chain is with a vector of probabilities, where the sum of the elements in the vector must equal 1. Usually Markov chains are initialized with the initial state distribution at step 0. It's pretty common for the initial distribution across states to be assumed as uniform, which intuitively just means we expect the user to start on any web page with equal probability. One of the key aspects of analyzing Markov chains is understanding how the distribution across states change at each step or point in time. This leads to a discussion on how we model transitions in a Markov chain. Let's isolate state 0 of this Markov chain and think about how the probability of landing on it after one step works out. In order to make this calculation, we need to know the probabilities of being in each of the 5 states of the Markov chain at the previous step in time. Once we have these probabilities, the probability at state 0 is essentially a weighted sum. We take the probabilities of each previous state, multiply them by the probability of transitioning to state 0 from that state, and sum over all the states. If you think about this calculation, it's essentially a dot product. We can extend this across all states of the Markov chain. If we take all the transition probabilities from state to state and fill them into a matrix where every row index corresponds to the previous state and the column index corresponds to the current state, this gives us a transition probability matrix. Now what's really nice about Markov chains is we can find the probabilities of landing in each state at the next step fairly easily. It's just a matrix vector product of the probabilities at the previous state times the transition matrix. Now, the problem of finding the stationary distribution can be formalized. A stationary distribution is defined as follows. Given a distribution pi, we define it as a stationary distribution if after the next transition, the resulting distribution is also pi. If this is the case, no matter how many transitions occur after this point, the distribution across states will never change. So another natural interpretation of the stationary distribution is that given a large enough number of users transitioning across states, once we reach a stationary distribution, the proportion of users that lie in each state will not change. Note that users will continue to transition to different states at each step, but the overall distribution of users across states will remain constant. Before we get into exactly how we might solve for the stationary distribution, it's important to address the question of whether a unique distribution even exists for a Markov chain. And another critical point to address in our model is if any initial distribution eventually converges to the stationary distribution. It would be hard to make decisions on ranks of web pages if multiple stationary distributions existed, or a stationary distribution changes based on the initial distribution of users among web pages. Let's start with the question of uniqueness. I challenge you to find an example of a Markov chain where multiple stationary distributions exist. This may seem like I'm throwing you off the deep end here, so I'll give you a hint. Think about a simple example with only 2 states. Suppose we had a Markov chain with the following transition probabilities. For this type of Markov chain, what's the stationary distribution? Well, if you think about it, given any initial distribution, nothing's really going to change because every state transition points to itself. More formally, the transition matrix is simply the identity matrix, so any initial distribution by definition is a stationary distribution. So this is where the first important constraint regarding Markov chains comes into play. This particular Markov chain has the property where if a user starts in one state, it's impossible for the user to get to some other state. These specific Markov chains are called reducible Markov chains. I know what you're thinking. And the answer is no, I did not make that name up. In fact, what we really want for stationary distribution analysis is irreducible Markov chains, which have the property that any state has a chance to be reached from any other state. It turns out that for any irreducible Markov chain, a unique stationary distribution always exists. Now the next question for irreducible Markov chains is if it's true that any initial distribution eventually converges to the unique stationary distribution. Let's take a moment to discuss what we mean by convergence. In this particular Markov chain, suppose we start off with the uniform distribution across all states. If we run our Markov chain simulation, after about 20 steps, we end up converging to a distribution which, take my word for it, is indeed the stationary distribution. Now what's remarkable is that for this particular Markov chain, I can start off with any initial distribution, say for example concentrating all the probability in state 0, and I still end up eventually landing on the same stationary distribution. This time it takes about 25 steps, but nonetheless it still converges. In a general sense, what we mean by convergence is that any initial distribution, after a large number of steps, settles into the eventual stationary distribution. My challenge to you now is to see if you can come up with a Markov chain where an initial distribution does not actually end up converging to the stationary distribution. This is a pretty hard task, but again, think about a simple two-state example. Here's the simplest counterexample. Suppose I have a two-state irreducible Markov chain where each state has a 100% chance of transitioning to the other state. What's the unique stationary distribution here? The best way to see the issue here with convergence is with two initial distributions. If we start with the uniform distribution across both states, all transitions will result in no changes, and this distribution is indeed the unique stationary distribution. But what if the starting distribution was 80% at state 0 and 20% at state 1? Now if we apply transitions, the distribution across states never converges. It simply oscillates between the two extremes. This brings to light a second key property of Markov chains. These types of Markov chains are called periodic Markov chains. We won't go too in-depth into periodic Markov chains, but there are a couple things to know. When discussing these types of Markov chains, we're implicitly assuming that they're also irreducible. The intuition behind periodic Markov chains is that if you imagine a user moving from state to state, there exists some regular interval greater than 1 between visits to a node. For example, in the above Markov chain, the period is 2, since for any starting state, it's only possible for a user to get back to the state in regular intervals of 2 steps. When Markov chains have this periodic property, it means that there exists some initial distributions that will oscillate rather than converge. If no such regular period of greater than 1 exists for each state, we can say the Markov chain is aperiodic. Markov chains that are irreducible and aperiodic have an incredibly cool and perhaps surprising property that no matter what the starting distribution is, as you continuously transition through the Markov chain, the distribution will always converge. In our web page example, what this means is no matter what the initial distribution of users is across web pages, as long as the Markov chain representing the web graph is irreducible and aperiodic, the long-term distribution of the users will converge to the stationary distribution, which, remember, provides a good metric to rank the web pages. It doesn't matter if all the users started out on a specific web page or if they were distributed evenly across all web pages. After enough steps, it is mathematically guaranteed to converge to the unique stationary distribution. This theorem is often called the Ergodic Theorem for Markov chains, and it forms the basis of many applications. This theorem, of course, requires a proof, but the details require a fairly strong background in probability theory, so for the interested viewers, I will provide a good link in the description to the proof. Now, the next natural question, of course, is how do we actually calculate the stationary distribution practically? The first way is perhaps the most straightforward method. We start off with an initial random distribution, and at every step we multiply the Markov transition probability matrix with this distribution. After we get the new distribution, we simply check if the distance between the new vector distributions is less than some tolerance that we choose. When this difference is small enough, we claim that we have found the stationary distribution. In a sense, you can consider this as a brute force method to find the stationary distribution of a Markov chain. The second way to solve for a stationary distribution is to utilize the definition directly. When we expand the definition, it features a system of equations, and if we can solve it, we have a stationary distribution. But there's one problem. If you try solving the system of equations, you will find that it's actually unsolvable. Two of these equations end up being redundant information, so you can't find a unique solution. The trick to solving the system of equations is to add in the implicit constraint that the sum of the individual probabilities must equal 1. By replacing one of the Markov chain transition equations with this implicit constraint, We can solve for the stationary distribution directly through a linear system solver. The final method is my personal favorite because it's quite a cool connection between Markov chains and some fundamental linear algebra. To understand it better, let's modify our state transition equation slightly. There's an implicit convention to define the Markov chain distribution as a row vector since it makes the transition probability matrix nicely correspond to the edges of a Markov chain. But another way to represent the updates of the distribution is through a more standard matrix vector product, where we now represent our distributions as column vectors and then multiply the transpose of our matrix by the distribution to update it. By treating every column of our original matrix as a row and multiplying by a column vector, we get the same dot products as before. Once we have this representation, if you think about these column vectors on a coordinate plane, we can observe how the updates change the vector over the iterations. And what we're looking for is a vector where applying the matrix P transpose results in the exact same vector. Assuming that this vector always exists for this matrix, what does this imply about this special vector? What property of P transpose does it correspond to? A core concept in linear algebra involves eigenvalues and eigenvectors. An eigenvector V of a matrix A has the property that when we take the matrix vector product A times V, it scales the eigenvector V by a corresponding eigenvalue lambda. If you think about stationary distributions from this perspective, we're actually looking for a very specific eigenvector, the one that corresponds exactly to the eigenvalue 1. A remarkable fact is that for irreducible Markov chains, the state transition matrix P transposed always has an eigenvalue of 1 with a unique eigenvector. So a third method for finding stationary distributions of a Markov chain is to simply find the eigenvector corresponding to eigenvalue 1 in the transpose of the state transition matrix. Once you have found this eigenvector, the stationary distribution is just a scaled down version of it that sums to 1. This connection between Markov chains and linear algebra really blew me away, and I wish it's one that was mentioned more often in a standard linear algebra class because it's one of the most natural applications of the concept of eigenvalues and eigenvectors. Throughout engineering, you'll often see that long-term behavior of systems is intimately tied to eigenvalues and eigenvectors. Markov chains just happen to be one good example of that. So, to take stock of where we are, we have a stationary distribution which is a good measure of the importance of every web page in a Markov chain. We now have 3 separate ways to calculate the stationary distribution. So here's an interesting question for you. Imagine we tried to find the stationary distribution of a massive web network of hundreds of millions of web pages. Which of these 3 methods do you think will perform best in practice? Let's say we tried solving a system of equations on this massive web network. The big problem here is in practice, solving a large system of equations can be quite expensive. In the worst case, solving linear systems tends to be a cubic time operation, which can be pretty slow when dealing with the massive scale of web networks. The eigenvalue method also has a similar problem in the sense that in general, getting a decomposition of eigenvalues with eigenvectors takes cubic time. So perhaps shockingly, practical experiments on web networks found that the first brute force method of calculating the stationary distribution often led to the best performance. It turns out that a lot of web networks have relatively fast convergence times. Most web search use cases converged within 50 iterations. Now again, this depends a lot on the thresholds of how much tolerance you have for error. The answer that you get in 50 iterations is not the true stationary distribution, so we are cheating a bit, but it goes to show the trade-offs that engineers were willing to make for something that is good enough. Sometimes a brute force approximation beats out clever algorithmic transformations. This is just an excellent example of an engineering mindset. In some cases, a good enough solution is a better choice than the perfect solution. The PageRank algorithm that built the first version of Google is fundamentally based on the principles of calculating stationary distributions of Markov chains, but there are a few important complexities that the creators needed to address. After all, web pages can do whatever they want, and one type of Markov chain that gives stationary distribution calculations a problem is web pages that have no outgoing links. As a result, all transitions to the state would never exit the state. The problem here is it's really hard to determine a ranking of the pages properly, since eventually all users traversing this network will just be absorbed into state 3. Another issue occurs on the following type of graph. It's entirely reasonable to have 2 or more web pages linked to each other in such a way where once a user enters, they get stuck in a never-ending cycle. Once again, if we try to do some sort of stationary distribution calculation on this network, it's impossible to rank the states since all users eventually just end up cycling between states 0 and 1. The big problem here is that a lot of our tools for calculating the stationary distribution and subsequent ranking rely on the underlying assumption that we are working with irreducible and aperiodic Markov chains. The question now is, how should we handle Markov chains that don't fit this property? The idea is remarkably simple, and it's a classic example of transforming a hard problem into one that we know how to solve. Let's think about this from the perspective of someone who surfs the web. Suppose a user ends up continuously transitioning to various web pages and then suddenly they hit a web page without any outgoing links. What might they do? Well, it's reasonable to think that they'll probably just find another web page to surf from the network. In more technical terms, they'll randomly select a new state from the Markov chain. And the way we can embed that idea in the Markov chain is really elegant. Going back to our earlier simpler example, the core solution is, at every step, with some probability alpha divided by the number of states, we'll end up transitioning to any random state in the network. You can think of this as a way to simulate the notion that a user might just get bored and go off and open a completely random page and then start surfing again. Now, it's not enough to just add these random transition probabilities, because you'll notice that it breaks the assumption of a probability distribution across transitions. Notice these distributions no longer sum to 1. So what we do to solve that problem is we add a damping factor of 1 minus alpha to all the existing transitions. In a sense, with probability of 1 minus alpha, we'll follow the original Markov chain transitions, but otherwise, will randomly teleport to a new state. This basically prevents any state from permanently becoming an absorbing state, and it also prevents users from being stuck in a cycle as well. Mathematically, what's going on here is we take our original transition probability matrix, multiply by the damping factor, and then add alpha over n times a matrix of all ones. Adding the weighted matrix of all ones simulates the idea of any random state being picked as the next transition. All PageRank involves is calculating the stationary distribution of this modified Markov chain. Throughout this video, we've discussed Markov chains, which implicitly require some background in probability. One of the best ways to learn probability and solidify understanding of these concepts is by interacting with them directly and solving hands-on problems. A great tool that provides interactive learning is Brilliant, the sponsor for this video. For those of you interested in diving deeper into Markov chains, Brilliant has an excellent module on probability at various levels. From introductory probability to practice problems with Markov chains, and even an in-depth analysis on stationary distributions within the context of quantitative finance, the resources offered by Brilliant provide a great supplement to this video. All of their courses come with elegant interactive visualizations and a great set of practice problems to encourage mastery of the content. You can get started for free by going to brilliant.org/reducible, which is linked in the description below. Brilliant is providing a special offer through this channel where the first 200 members to sign up get 20% off the annual subscription. It's a great way to learn more about the topics in these videos and also a good way to support this channel. Big thanks to Brilliant for sponsoring this video. So to put everything together, we start off with the web network, which can be interpreted as a Markov chain. PageRank then tries to find the stationary distribution of a slightly modified Markov chain where the transition probability matrix is updated by a damping factor and also accounts for random state transitions. This final matrix is what PageRank then uses to calculate the stationary distribution by performing iterations until the distribution converges up to a tolerance. This final distribution then provides the information needed to make a ranking for web pages. It's not an exaggeration to say that PageRank may be not only one of the most lucrative algorithms ever created, but also one of the most important in terms of defining the domain of search. Most of you now know the remaining parts of the story. Larry Page and Sergey Brin went on to found Google, and the rest is history. Thanks for watching, and I'll see you all in the next one.